1.5. Most of this is a lot of vocabulary that's in the book. You should have got if you interchange, to verify an inverse, what you're going to do is that f and f inverse and f inverse and f, these are called the composites, are equal to the identity function of x, and we talked about that identity function. When you do a composite and you get x in both directions, it means they are identities of each other. So here I have the f inverse of x is x over 4. So if I'm going to do f of f inverse, I'm going to get 4 and then x over 4, because I know what the inverse is. I'm going to put the inverse into my f equation, and that's what, there's my 4 of x, that's the equation we're talking about, so that I get x. And then when I put x into my inverse, so my x is 4x, and when I put it into the inverse of over 4, it reduces to x. This proves that they are inverses of each other, because when we do the composites of them, we get the x, or we get the identity. Let f and g be two functions such that we talk about their domains, we talk about their inverses. The domain of f must be equal to the range, and the range must be equal to the domain, because when we do inverses of each other, the domain and range switch with each other. If f is the inverse of g, then g must be the inverse of f. So here I have a function, f over x minus 2, and we want to know which one is the inverse. Well, in order to find the inverse, we do have some algebraic steps that we take to do that, which is going to be happening on page 5. So we're going to kind of jump ahead here to page 5. And what it basically says is that we are going to switch x and y. So in this case, for the example that we were working on, page 2, we're going to switch x and y, remembering that f of x means y. So x equals 5, y minus 2. And then solve, back to page 5 there, we're going to solve for the new y. In this case, I'm going to multiply the x and the y minus 2, which essentially means I'm going to be switching locations here, because when I multiply by y minus 2 and then divide by the x, it essentially means that they're going to switch places. And then I can add the 2 over, so 5 over x plus 2. We find that h of x is the inverse of my original function. All right, on page 3, if AB is a point and it lies on the original function, then BA has to be on the inverse, and that's what we just got done talking about on page 2. Even though I didn't write it down, and actually page 1 shows it. If xy is a function of f, then yx, they're going to switch locations, becomes the domain and range of each other in the inverse. And that's what happens here. So what that means is if AB is on F and BA is on the inverse, then these are going to actually be reflections. The function and the inverse are going to be reflections of each other over the line y equals x. And just very quickly to, look at a very simplistic version, let's say you have the point 2, 1, and that's your function. Well, then when you flip those, 1, 2 is going to be on the inverse function, 1, 2, and the equation y equals x goes, through the origin, 1, 1, 2, 2, and they are going to be mirrors of each other. So that's just a very, very quick showing of that. We're going to look at some more examples of that. Here we're going to verify that these are inverses of each other, and the way we do that is we do substitute one into the other. F of g, g of f, and each time we need to come up with that x, that identity. So I'm going to replace the x, with the g, so that's going to be f of g. So I get 2 cube root x plus 1 minus 1. Well, a cube and a cube root cancel each other, so I get 2, and the cube root x plus 1 over 2 minus 1. The 2's reduce, the 1's reduce, leaving just the x. So now when I go the other way, g of f, I'm going to put the f equation all into the g. So here I'm going to get the cube root and then replace the x with f. So the 1's go away, the 2 cancels, so the cube root of x cubed is just x. We've proven that f and g are inverses of each other because they have the identity function of x and x. Numerically, I could prove this. So this is algebraically. Numerically, I can fill this in by doing my substitution. I can put -2 into the x and then come up with what is my f of x. So if I do that, I get -2 cubed minus 1, -8, -16, -17. Then I can do it for 0. Well, that's minus 1. And then I can do it for 1, and I can do it for 2, and I can do it for 3. And if I go and now reverse it, because technically I should be able to, if they are inverses of each other, the domain of f is the range of g, and the range of f is the domain of g, because they are going to switch places, because that's what it means to be an inverse. So if I plug -17 into g, -17 plus 1 over 2 is the cube root of -16 over 2, cube root of -8, which is -2. It works out. And then I could fill in the rest of these. This is going to be 0, 1, 2, and 3. So when I go to plot these points, and I'm not going to go too far with this, graphically I'd probably just pull out my calculator. Y equals, and the first one is going to be 2x cubed minus 1. And just look at that, what that picture looks like. We get something resembling this, and that's our f equation. Okay. Now if I put in the g equation, the cube root I get under math. Option number 4, cube root, and it's going to be x plus 1 divided by 2. Watch your parentheses. And notice we get something that looks more like this one, something like that. And that's our G equation. So what happens is that these reflected over the y equals x. The point that was here is now on the inverse of the other. Point, 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 point. And that's what it means to reflect over it. I could bend my paper in half along that y equals x line, if I were to do that, and they should lay on top of each other. That's what it means to be able to be a reflection of it. If I were to bend my paper, they should lay on top of each other. Or every AB in fx becomes the point BA in g of x. So graphically, numerically, algebraically, we've done 3 of our 4 NAW process. All right, page 4. The existence of an inverse function. How do you know that an inverse function even exists? Because some functions do not have an inverse. Here we have a table of values. And when you interchange the rows and tables, meaning flip them, make the x's the y's the x's, our outputs do not correspond to the same inputs. So we say f of x, in this case, f of x equals x squared, has no inverse. In order to have an inverse, a function must be 1 to 1. Short version, instead of writing out the words, just 1 to 1. For A and B in its domain implies that f of A equals f of B. In existence, a function f has an inverse if and only if it is 1 to 1. Now, we can tell if a function is a function by a vertical line test. Do you remember back? We would look and we would say, oh yes, it's a function because it passed the vertical line test. Well, in order to know if it is a inverse exists, it has to pass the horizontal line test. All right, and if I run here a parabola, if I run the horizontal line test, notice it hits twice. That's why the x squared up here does not have an inverse. This parabola will never have an inverse because no matter what, when you run that horizontal line, it's not going to be 1 to 1. It's not going to hit only one time. So no matter what, anything to an even power, because there's a square, there's a 4, there's a 6, they are never going to be 1 to 1. They will never have inverses. 2 special functions that pass the horizontal line test are those that are increasing or decreasing their entire domains, such as a line. That will always pass a horizontal line test, therefore it will always have an inverse. I already talked about this a little bit earlier. Whenever we're trying to find the inverse algebraically, we make our f of x y, that we're used to doing, and then we switch that x and y to solve for the new y, and then we put in proper notation. That's all this is. Just put back proper notation. If the domain of f is assumed to be the entire real line, It is possible for a function that has no inverse when the domain is set of all real numbers to have an inverse where its domain is restricted. So I could go from everything to restrictions. So here's a function. We're going to find its inverse. The way we're going to find its inverse is we're going to do it algebraically. We're going to make f of x y. We're going to switch our x and y. And now we're going to solve for the new y. So I'm going to multiply by the 2. I'm going to subtract the 5. And divide by the -3. And so that's going to equal my y, but proper notation says that that's actually f inverse. So make sure you put proper notation. If you put down y, you will lose points for that. You need to make sure that when you start in function notation, you end in function notation. So we use the y just for the work, but in the end, it needs to be in proper notation. Page 6 here, we have a square root. We're going to find the inverse of that square root. To find the inverse of the square root, we go through their algebraic steps that we just talked about. Change our f of x to a y. Switch our x and our y. Now solve for the new y. So I'm going to square both sides so I can get rid of the square root. I'm going to add the 3. And then I'm going to divide by the 2. And I'm going to put it in proper notation. Now, I do need to be very careful with this because my domain of f was restricted. Because it was a square root, its restriction had to be greater than or equal to 0. If I put that in, 2x minus 3 greater than or equal to 0, we add the 3, divide the 2, we get that the domain of our original function was restricted at 3/2. So let's look at the picture of the original f of x. It started at 3.5, and let's look at see if we can get a little bit more accurate points. Square root of 2x minus 3. It is going to start at 3/2, or 1.5. I'm going to go to my table just to get some exact points. The value of 2 gave me the value of 1. The value of 6 gives me the value of 3. 1, 2, 3, 4, 5, 6. 1, 2. Okay, so there's my f equation. The domain was restricted from 3/2 to infinity. And if I look at the range of f, well, it starts at 0 and goes to infinity. So now when I look at my my inverse, f inverse, these have to be reversed. The domain should be 0 to infinity, and the range should be 3/2 to infinity. So let's look at the picture of it. We know what the equation is because we just found it. So let's type in the equation. Y equals x squared plus 3 divided by 2. Look at the picture. And we are going to only, because our domain is restricted to 0, we are only looking at this, and again, go to our table so we can find some exact points. 0 is 1.5, 1 is 2, 3 is 6, which were the reverse points of what we had here, because it will reflect over our line y equals x, and that's our F inverse. Again, if I were to fold the paper on top of each other, you would see that the F line gives me my inverse line. The domain and range of my function is, switch them, the domain and range of my inverse. And that's always going to be that way. And when you are asked to graph them, you need to use at least 3 specific points. Don't just guess it and don't just draw it down. You need to use some specific exact points. And I'm not talking big points at all. They just need to be relative to each other, and it needs to be close, and it needs to make sense. So that will conclude 1.5.